just mentioned, there's 3 weeks left in the semester, 3 chapters left, and we'll do what we can to get through Chapter 8 today, tidal, maybe have a little bit more time for it. And then there's one other thing I hope I can get to by the end of the lecture. So here we are looking at a tidal technology. One thing to note about tidal technology is that, yeah, it's carbon neutral. Nothing's being set on fire in this case. It's very similar to hydroelectric, except in this case we're not relying on the sun to evaporate water and then the cloud to form and then the rain to fall and come down a river. In this case, we're just relying on the fact that tides happen. And I think there might be a problem or two in your text, but one thing I do want to cover is Newton's law. So if we look at the force of gravity, that equals Newton's constant G, m1, m2 over r squared. And the reason that's important, and this is sort of what causes tides to happen, is that if the Earth is here, and I'm just going to call this the sun or the moon, because we've got solar and lunar tides. There's this effect. You have the force equals G m1 m2 over r squared. So on this side of the Earth, you've got more pull and greater bulge, and on this side, you've got less, and that's basically what's causing the tide. So I think we've seen that previously. Just wanted to clarify that. That's where it's coming. It's coming from gravitational energy, and there's the force. Okay, so here's an example. Tide comes in, it's raised enough, and you've sort of got a one-way valve. The turbine creates electricity, and then back to the ocean. So there's your sort of renewable cycle, if you will. Here's a shot of one, and so we've looked a little bit at that Gordon Butte pumped facility. This is similar, a little bit smaller, but you can see where they've taken advantage of a natural occurring phenomenon, a natural feature to sort of, let nature take care of some of that ramping of the water uphill, if you will, for generation. Here's the 3 steps or 4 steps. So initially there's what nature looks like. You dig your hole, make your device, and then finally it's completed. So the key being here, let's do the work before we let the water in. In this case, we're looking at a technology that actually, instead of having water go through a turbine, they're actually just compressing air. So that top reservoir is just allowing air to oscillate back and forth. So when that happens, you can then spin a fan, and the fan can spin forward or backwards. And again, when you spin a fan, attach that to a generator, you make electricity. Here's another example. Shot of one. Almost all of these are coming out of England. There's a person standing up there for the scale. All right. So rather than a steady stream like we see with hydro or like we see with wind, in this case we're dealing with oscillations. And in this case, the higher the wave and the more frequent it happens, the more energy comes in. And here's several zero crossings. It's just showing the sum of each of those. Okay. All right. So this chart actually has a lot of meat to it. So let's spend some time looking at this. if, okay. So here again, the higher the wave, the more energy that comes in, and the more frequently that wave comes in, the more energy it has. So what we're kind of looking for, and it's similar to that distribution we did with wind not too long ago, where we were looking at how frequently wind of a given speed comes in. So does anybody have the textbook with him? I was just going to look for the equation there for wave power. Here's power equals rho g squared h squared t over 32 pi. Thanks. Oh, I think I just realized, I think I was saying tidal, and this is the wave chapter. Thanks, anyway. Chapter 6 was tidal, sorry about that. Like, wait, I think I already covered Newton's. So, anyway, if we just go back, yeah, let's just go back really quick. Sorry about that. Yeah. Go back. The technology is similar, but what we're really looking at is something where a wave comes uphill, goes in the reservoir, rather than, so I guess the point is, then what I misspoke on earlier, is that this technology, unlike the tidal technology we saw before, happens more frequently on a minute by minute, second by second basis, rather than on a twice daily cycle. Okay. Thanks. Okay. Yeah, and so these technologies are typically a lot smaller. Oh, and one other thing that is worth noting, this is not all that intuitive. So if we take sort of a top view, here's land, here's water. If you think back to that first paper in Energy 101 where we looked at energy on a joules per cubic meter basis, the way that wave energy is typically rated, it's a kilowatt per meter basis. So if you say I've got this much ocean front, lakefront, etc. You can imagine doing this even up on Flathead Lake. Some of those days, those waves can hit 3 or 4 feet. A lot of energy there. It's kilowatts per meter. So if you say, hey, I'm going to build a 1 meter wide, 2 meter wide, 10 meter wide technology, multiply that by the kilowatts per meter, and then you can say, okay, you've got a 1, 2, 3 kilowatt device, etc. So that's the key to think about. All right, so now if we go to our resource map, just go back here where we were, we can see that down here, let's just look at our power equation. Let's look at our power equation. And actually, let's just do a really quick dimensional analysis on this guy. So if rho is density, that's going to be mass per length cubed. Gravity is length over time squared. Height is length squared. And then the missing guy here, this t, it's listed as a period. So you can see here's the period, and the units are just follow right after it per second. So the units on period are in hertz. It's how frequently that hits. So if we do that one more time, 1 over time, then of course 32 pi is dimensionless, and so we end up with, let's see, so we've got mass, so power, let's do this, guys. So we've got mass, we have length cubed over time squared. Okay, something's wrong. What did we do wrong? Oh, gravity squared. I forgot to square gravity. So mass, let's see, length. So let's square length. And then t to the 4th. Erase that. It may turn out that we have to flip the units on that t. Okay, I've got gravity right now, so I've got length to the 4th over t to the 5th. That t is going to have to flip. Let me just see here. Let's just take a look. Energy period. Because this guy is, as I said before, there's your kilowatts per meter. There's your height. Okay, so density again, mass per length cubed, gravity squared, so it's length squared over time to the 4th. H squared, that's going to be L squared, and this is time. That time has to flip. Is that what you're seeing in your textbook too, Mariah?
Which one?
Does it actually give the units of t?
Let's see. It doesn't right here.
So I think what we're going to need to do.
Period just be in seconds, like shouldn't it just be time?
I mean, it really should.
Yeah, so instead of 1 over t, shouldn't it just be t?
Yeah.
It says the most frequent occurrences are at HS 2 meters and TE 9 seconds.
T equals 9 seconds. Okay, so in this case,
Yeah.
t is going to be in seconds. You could obviously flip it and just call it tau, which would be the time constant, and put it in hertz. So in this case, we can see from our dimensional analysis that t has to be in seconds. So from there,
So it's just t.
yeah, so let's simplify. So we got mass length over t cubed. And if you remember, power is mass length squared over t. So we're essentially missing a length there, which makes sense because right there you've got kilowatts per meter. So the dimensional analysis bears out exactly what we were doing. So this is power per meter. All right, this guy's misbehaving. I'm going to have to reboot in a second. But let me just finish this last little bit up. And so what we're looking for is, so if we take this t, so for example, you could imagine putting 22 in there. There's your height, you know, the density of the water, and from that you can get the power from that little chunk of the graph. Way out here, a wave of this height happens relatively infrequently. You know, this guy way up here is basically a tsunami, but it only happens very rarely. This stuff down here, much more frequent. Here's your 42, but just not as much power. And again, you can see that each of these guys, 5, 10, 20, 50, this is all in kilowatts per meter. Okay, so hopefully that all makes sense. Yeah.
In the problem set, it wants you to derive the equation h squared, so height squared times t,
Yeah.
or equal height squared times period.
Yeah.
I'm not exactly sure. Did we get to that?
Not yet, but we can. Yeah, but let's.
Okay.
Yeah. I just want to get through this one last set of figures for wave energy, and then I'm gonna reboot, and then I will look at that problem with you. Sorry for the technical difficulties. Another thing to note is that waves can travel in multiple directions, and so what they're showing here is once you've sort of summed, you know, a wave that might be coming from, you know, the wind, it could even be coming from a watercraft, a lot of different places. Once you've added them, you get a surface that looks a lot more like this. Also, just like we saw with wind, if you're looking for wave resources, typically they have a direction. You know, if you're over there at Flathead Lake, you'll notice that typically the eastern shore is a lot wavier. You know, the weather sort of comes from the west, and that's just simply because all of that air is sort of, you know, rising up against the Rockies and doing that swirl. So this would guide you in terms of the directionality of the device that you're going to build. Another thing to note is that the waves themselves at the surface, there's a little bit of horizontal, but the majority of the motion in the wave is vertical. When the wind blows, it doesn't blow the lake away. The lake is still there. So on average, the water never really moves, and what we're seeing here is just a bunch of circles. Once you get to the beach and you get that big, you know, rip curl and all that, it comes in, but that's, you know, relatively modest transport comparatively. Okay, and then this is showing that the waves themselves diffract a little bit. So just like when you see light go through a prism, light diffracts. As the wave comes on shore, it's also being bent a little bit. Just there on the beach in San Diego, and heard the lifeguard saying, "The riptide is real." And so, you know, so basically, what goes in must come out, you know, must go out somewhere. So this is just showing as the water comes in, it is, you know, bent a little bit. Here's an example showing sort of the convergence near the shoreline that's protruding, and more or less a divergence. So if you've got a chunk of shore where there's an inlet, the water's going to go somewhere, so it's going to go out in all directions. Water is incompressible, unlike air, so this expansion causes that contraction, more or less. This is looking at wave resources in the UK. So as we see more and more of our energy going towards offshore, that's what's going to happen. And now a few technologies. Also very, very key here. Just thinking back very briefly to our wind turbine technology. This is essentially the only thing the wind turbine is doing, right? It's spinning. It's pitching again and again and again and again, spinning. But in the case of a wave technology, you can take advantage of the fact that any object, and again, right here we're just in 2 dimensions. We're not in 3 dimensions, but so again, in 2 dimensions, an object has 3 degrees of freedom, and so what we've seen is the first one, it can rotate. also go up and down, and it can also move front to back. So if your technology can take advantage of all three of those modes, those three modes of motion, you're going to do better than someone who's just doing one of the three. Make sense? If you're actually in 3D, you then have 6 degrees of freedom because you can move back and forth, and you can also spin about 2 other axes. So a lot of these new emerging kind of weird-looking wind turbines, water turbines, are taking advantage of all of those directionalities. In fact, when I was on that little tour with my daughter, one of my classmates there has his own offshore wave technology, and everything's below surface. And he's got a interesting metal that creates electricity when it vibrates. I can't remember the name of his company right now off the top of my head, but the idea is we're just allowing that metal to deform and generate electricity. And it's through a phenomenon called piezoelectricity. And piezoelectricity, it's like a quartz crystal, the same way that all the microphones and speakers work in a lot of electronics. Mechanical compression gets turned into an electrical signal. Yeah. Okay, so now we're seeing, just as we did with the wind chapter, now we're seeing a lot of different types of wave turbines. Some of them, again, here's just sort of your up and down. In the case of these buoys, you can also seal it, so you've got some kind of hydraulic fluid being pumped back and forth. In this case, the raft is keeping this guy stationary as it moves back and forth, supplying energy. Every one of them is tethered in some way, if you're actually going to tap this and grid tie it rather than just running something offshore. Here's another one that's just simply rotating back and forth. I also mentioned you might have an air turbine instead of wind, just because the water is incompressible and the air, as it moves through, has to go somewhere. Another air turbine, and then the tap chan. This is what we looked at very early on, where the tapered channel causes that wave to sort of rise up, and then here goes your turbine as it comes back through. Okay, so I'm going to take a little break there, and I'll look at that problem with you.